This tiny little cube reacts to chemicals in the air. When was the last time you opened the window to ventilate your room? Seriously, was it today? Was it a year ago? Because I didn't think about this at all until this happened. I feel affected physically. I actually don't feel good. We can't see air, but it can. And we will do some experiments. Do I want to do this experiment again? And I'm gonna walk you through the engineering behind this little beauty, because there were some really cool gotchas that caught me by surprise, to be honest. Now, VOC sensors are not new, but none of the ones on the market just checked all my boxes. So I built my own. I wanted something that's hackable, expandable, and most importantly, open sourced. I call it the Air Cube. It's super simple. It communicates to you via color. That's it. There is a USB serial port exposed, and it actually spits out quite a bit of data, but I'll get into that in a bit. But getting to this stage, oh boy, there were quite a few bumps I had to encounter, and things did not go as planned. But first, let's get into the first experiment. Car is off. I'm locking myself in the cabin of the car without any ventilation. Both windows are up. I want to see what happens with VOC levels over time. All the way up. I bet you this will be less than 30 minutes and this thing is going to be orange, but we'll find out. For now, back to the engineering. We'll check in just a few minutes. All right, let me finally show you what's happening inside this little box, because it is awesome. Inside the board, we have a VOC sensor. And VOC sensors are basically electronic noses. That's how you can think of these devices. They sense organic compounds. The way that VOC sensors work is, in essence, by measuring resistance change over a hot plate. When a volatile organic compound hits the plate, the resistance changes, and therefore your VOC count goes up or your VOC count goes down, depending on how many volatile organic compounds are hitting that sensor. Cleaners, breath, smoke, or any other volatile organic compound, and the sensor reacts. Okay, so it's been only 5 minutes. This is actually kind of worrisome because the cube is quite yellow. I'm not feeling any effects yet. To be honest, the air kind of feels okay still at the moment. I'll update you in a few minutes. For now, I want to get the Python script going so I could actually log some of this data. I was hoping this would happen much slower than it's happening. This is kind of crazy. All right, for this project, I went with the ENS161. It is one of the best VOC sensors on the market today. But here is something that almost no one tells you about these sensors. As we discussed, VOC sensors measure a hot plate and the resistance, right? So if your temperature, your ambient temperature, your room temperature goes up, well, so does the actual reading, or rather the reading gets skewed, because you're measuring a hot plate. So that hot plate becomes hotter. And majority of the sensors will actually spike in VOC count, even though your actual VOC count has not gone up. Fortunately, the ENS161 accepts temperature readings and humidity readings. Those two readings are fed into the 161, the ENS161, to compensate algorithmically for the VOC count from artificially just going up or down, which is great because these have been super stable. So that's why I actually have two openings in my sensor, in my actual cube. One is for temperature readings. I want to know the ambient. And the other one, well, that's for air quality. But that's actually where I kind of ran into an issue. Because I wanted to communicate with LEDs, well, LEDs heat up. And because I wanted to have an ESP32 inside, well, ESP32s tend to run hot. And the VOC sensor itself uses heat, right, to warm up the resistors that it actually uses to determine the actual VOC count. That raises the cube's temperature quite a bit. And that's where I ran into a few gotchas on the PCB design. So it's been, what, 10 minutes at this point, more or less? And the cube is starting to become orange, which means the air quality within this cabin, within this car, is starting to really be bad. I'll probably do another 10 minutes of this, but not more. All right. The heat from the ESP32 and the LEDs was traveling through the board and messing up my temperature and humidity readings completely. I knew I have to be cautious when designing the PCB, but yet I still managed to screw up. I did have slots on the actual PCB. They're tiny, that's one of the problems. And I did separate the sensors as much as possible from the rest of the circuitry, from the things that actually heat up. But the rookie mistake I made, well, I poured copper throughout the whole entire design. And copper usually is a great way to minimize EMI and all sorts of noises on the board and so forth. But unfortunately in this case, well, it acts like a heatsink. So for the second revision, I made the slots in the PCB much bigger. And I removed the copper. Basically, I just extended it barely above the ESP32, just to give that area, the fast signal area, enough EMI grounding and so forth. And check out the difference. The heat signature is much nicer. But there's yet another problem, because I wanted this to be a cube. Well, and all the electronics are inside. This basically became a hot box. Anything that's inside was just concentrating and heating up the whole entire thing. So here's how I solved it. I added a wall separation to the temperature sensor and the VOC sensor. So basically, I made tiny little chambers for both the VOC sensor separately and the temperature sensor separately. I wanted to separate it from the rest of the box. Now it's not ideal, right? It is not foam insulation or anything, it's plastic insulation. But it still does quite a good job. Now there was still one more problem to solve, because I wanted this cube to look quite nice and I wanted it to be easy for anyone to 3D print this thing. I didn't want a sharp glow and something that looks like a night lamp. I wanted something that just gives off a gentle little glow. And sounds simple, right? Here's what I tried. But first, let's check back in on the car experiment. So this is kind of crazy because we're almost hitting 200. I feel affected physically. I actually don't feel good. I'm gonna call it. All right, ready? Let's open that window. I'm gonna display the graph on the video. All right, windows open. Woo, 421 exact. Let's see how quickly we're able to get the temperature, or rather the air quality, back to good levels. Because I don't think I'm gonna have to speed this up at all. It is crazy how fast it's going. Wow. Temperature is dropping too, obviously, because I was inside, it was stuffy, right? It's bad air quality. And look at this dip. This is nuts. Oh, and it feels so good to breathe fresh air. Oh, we're below 100. Well below 100. We're rounding off. I bet you we're gonna go down to almost 0. Wow. Do I want to do this experiment again? I don't know. While I definitely do not want to do that experiment again, what I am going to do is put the cube inside of the 3D printer while it is printing with PLA. I'm very curious to see how affected that air quality is inside of that printer. Now, I'm going to also log the data, but for now, let's go back to the engineering. In a past project, I made a diffused glow effect. I wanted to light up the desk. And I experimented quite a lot with translucent 3D printed diffusers. Here's the problem. They look pretty bad. You can see all the lines, all the layers, the weird gradients, and well, it looks cheap. So I decided to experiment. I printed a really simple, thin, white plastic cover. And that, surprisingly, looked quite good. With a millimeter thickness on the top and a 2 millimeter thickness on the bottom looks completely opaque and the top glows in a very, very beautiful color. In my PCB design, I did point the LEDs upwards, but I, to be honest, did not expect it to look this good. But then I forgot about one thing. You know, I want this to be a plug and play, completely plug and play, but there needs to be a tiniest bit of an adjustment possible, right? Not everyone is going to be in a bright room. Not everyone is going to be in a dark room. So I thankfully provisioned for a button on the back. While I did not know what it's going to do at the time, I made a button on the back. And to be honest, the design here, maybe not perfect, let's put it that way, but it works. Oh, and the best thing, do you remember I mentioned the serial protocol exposed on the back? Well, that allows you to actually collect data over the serial port, graph it, log it, do whatever you want with this data. Plus, hey, this thing is actually based on an ESP32H2, which means BLE and Zigbee, well, they're inside of here. And that's why I actually chose an ESP32, because I want to integrate this little device with Home Assistant. I use Home Assistant for all my monitoring of the entire house, my switches and everything else. But that's coming. That's not there yet. And maybe potentially I'll make a video on that in the future. All right, to the experiment then. There we go. We are at currently around hovering at 30 some air quality index from 0 to 500. And I'm gonna go ahead and place the cube inside of the printer. Now I know that this cube will be safe right here. So no worries, it's not gonna affect my print, it's not gonna hit the print. And I am actually printing cubes themselves. So hey, 2 in 1. All right. So the air quality definitely is decreasing. The air quality index is going up. That means it is getting worse in there, as you'd imagine, right? We are, after all, melting plastic, and plastic off gases and produces VOCs, harmful VOCs, let's put it that way. So it is always a good idea to just keep your window open or just a fan running, circulate that air instead of just simply sitting here and breathing that, because it is, well, it is toxic. We're averaging mid-60s at the moment and we just hit 70. Wow, okay. Well, let's see how far this can go. Oh, wow. Okay, 110, 120. I mean, I guess, what was I expecting, right? 140s, 100, almost a 50. Okay, I guess we're not done yet. This is kind of crazy. Okay, so it looks like 150 is the maximum we've hit. We're sitting at 130 now, probably circulation of air. The fans started speeding up or whatnot, right? More circulation inside of the printer. So let's see how quickly the air quality goes back to good after taking out the cube. Let's just do a quick experiment. I don't think we're gonna go higher at this point. I'm gonna put the cube right by the window just to speed things up a little bit. Okay, now we're picking up some good fresh air. The numbers are dropping very, very quickly. Yeah, we're 70s already. It's a very drastic, sharp drop. Yeah, we're below 50s, we're back to green. Okay, that was actually really, really interesting to watch. So it just tells you, hey, you gotta open that window. If you're 3D printing, you're producing VOCs and they're harmful. Okay, I just got one more thing to say, so let's go. I do feel this cube is actually worth the attention. So I've actually decided to turn this into a real product. I've been using this now for quite some time and I love it. When my air goes stale, I get a gentle reminder and it's there sitting quietly on my desk. It's noticeable. It's not buried in text or numbers. And I open the window, I ventilate my room. I get my brain going again. It's surprising how quickly this air goes stale, especially in an office environment in a small spot. So if you want one, they are now available on my website, StuckAtPrototype.com. I make them here in my lab. I limit the number of quantities because, sorry, I just can't keep up. It's kind of crazy. So if you want one, if it's available, grab it. I'll put a link in the description. And as always, thanks for watching. Subscribe if you haven't, and I will see you in the next one.